board here. Hello, everybody. Welcome to the 7-2 class meeting and chapter 9 discussion. We're going to do some review real quick. Got some questions on some chapter 8 classwork. Number 20. Okay, it says indicate the hybrid orbitals used by each carbon atom in the following compound. So we'll go over this, but just so you know, on the test, I don't ask you about hybridization, sigma, pi, and all that kind of stuff. Your book gets a little bit more into it than is really needed for high school. So take a snapshot here. So basically, when you look at this, we're looking for sigma, which is s orbital overlap, and we're looking for pi, which is either s and p overlap or p and p overlap. And so basically, anytime you see a double bond, that's a pi bond. Anytime you see a triple bond, that's a pi bond. And anytime you see a single bond, that's usually a sigma bond. So it really depends on your particular thing. So in the case of the CH3, right, then we have the sigma bond here because this is going to be our s orbital overlap. And then we have the p's over here. But when it comes to this guy, it's got a sigma bond up here for the hydrogen, but then the double bond is a sigma and a pi, so it's a hybridization. So we just say that's a pi bond. But again, you don't need to know how to do that. It's really not very interesting for high school chemistry. If you want to take organic chemistry in college, you can worry about sigma pi bonds, but that's it. So, basically, the simple answer is single bonds are usually just considered sigma, and then pi bonds are considered pi. But then there's some also rules about like adjacent to pi bonds can be pi. So there's it's just not for your guys' level. So even though it was in the reading, I don't test you on it, so don't worry about it. And you'll notice in the quizzes I try and make like the test, and you'll notice in the quiz it doesn't talk about sigma or pi or any of that stuff. Anything else? I think the quiz closed, but let me see. So, yeah, if we go to the covalent bonding quiz, it's just like how many electrons are in a Lewis dot model, Lewis dot diagram. So the lithium should just have one. According to the octet rule, it's like atoms want to have 8 electrons. So you can see there's no like, sigma bond stuff, that kind of thing. Because again, that's really not needed for this level. So, and then they just wanted you to draw dot diagrams. Like what's the correct Lewis dot structure? What's the correct formula of carbon dioxide? How many lone pairs are in ammonia? That kind of thing. I just want you to really be able to like draw the dot structures and then make the structural formulas. And then I'll ask you a couple questions on the side, on the shape. I thought there was one question on shape on here, but I must have cut it off to be 20 questions. But either way, from last time, you remember we talked about the shapes. So I would just, it would be a simple question like, methane probably has what shape? And well, it's got 5 atoms, so the only shape it can be is Vesper. So when you're taking the test and you got your stuff out, you're like, oh, what was the 5-atom shape? Oh, it was tetrahedral. So that's the only thing it would be, tetrahedral. So, or there might be a question like, say you have a thing that doesn't have, you know, a shape to it because this has 8 atoms in it. So the question is like, what are the possible bond angles in this shape? So the answer is, we'll just draw the shape. And we have the carbons like this, and then we have the H's like this. And so the question is like, what do you think the possible bond angles are? Well, just look at it like this way. Well, if you imagine that you just kind of like cut this off, right? Then isn't that a tetrahedral? And if you put this on here and you cut this off, then isn't that a tetrahedral? So this just looks like 2 tetrahedrals put together. So all these bond angles are probably all 109.5. So that's kind of one of the things they ask you to do. It's just kind of like looking at, you know, a particular molecule. What do you think the bond angle might be? So here's a good example of that. Acetic acid is C2, CH3, draw today. Or sorry, H, CH3, COO. Well, what does that look like when you draw it out? Well, it looks like this, where you have the CH3, and then you have the C, and you have the double bond O, and then you have OH. So this is acetic acid in the Lewis, in the structural formula. And it says, what do you think the possible bond angles are for this thing? So I didn't ask this complicated of a question. But basically, if we were just looking over here, right? If we were just going to look at these guys, well, this is an oxygen as our center atom. So this bond angle is probably bent. So this would probably be the bent bond angle of 104.5. And if we look at this guy here, this guy has 1, 2, 3, right? So this, if you have a center atom with 3 things coming off of it, that's either going to be planar or it's going to be pyramidal. Well, the carbon has nothing left over. So these bond angles are probably the pyramidal ones. So these are all 104.5. And these would all be 120. And then when you look over here, well, this guy right here is a big tetrahedral. So these guys are all probably 109.5. So that is like a very, very hard question that I would ask, but you don't have, I'm going to ask like, you know, something simple like 2 tetrahedrals put together. What's the possible bond angle, you know? So it's simple. And if you want, you can obviously dump that, you know, what is the shape of of that molecule? Like, so say for instance, you know, you wanted to see that in 3D, then just go ahead and type in, you know, 3D model, and then you can kind of see C3. I did C3H6, C2H6. So then you would type that in and be like, oh, okay, look, it's 2 tetrahedrals stuck to each other, you know. So it'll tell you the bond angles. Any other questions, children? You can tell where the stuff on my screen is that you guys can't see because I didn't delete. Okay, so if you guys think of anything while we're talking, just let me know. Pop it up in the chat or do your hand raising thing, and we can chat, whatever you want. I'm here for answer questions for you, not just lecture on the next steps. But if there's no questions, we can move on to nomenclature. Nomenclature is a fancy way, if I can spell today, nomenclature. Nomenclature. Nomenclature is a fancy way of just saying naming system. Many things in life have naming systems. For instance, here in the United States, we tend to call each other by our first name. And if it's formal, we tend to call ourselves by our title and our last name. And where we get our last name has a system, and where we get our first name kind of doesn't have a system. It's just kind of chosen. But then depending on your culture, you might have reasons for your first name or reasons for your middle name. So those are naming systems. And then if you guys remember in biology, you had the kingdom, then you had the phylum, and then you had the class, the order, the genus, and the species. So, you had the three kingdoms, and then they all had different phylums. And in those phylums, you had orders, and then you have a particular genus, and then that genus might have a couple species on it or whatever. But that was a naming system. Taxonomy is what they called that. Well, for chemical compounds, we have a naming system because we need to tell them apart. So when you have something as old as time like water, when we say water and its chemical formula H2O, that's synonymous. That element has been around forever. So now that we know its chemical formula H2O, we didn't change its name from water. But when you look at salt, well, salt was just any name for any crystal that looked like salt. But then when we got into it and actually analyzed what salt was, well, salt was all kinds of things, but mostly it was sodium ions and chlorine ions mixed together in what's called sodium chloride. And then there's also a lot of calcium sulfate. There's calcium nitrate. There is sodium sulfate. There's all kinds of things. Like if you buy sea salt, there's these different types of salts in there, not just sodium chloride. There's potassium chloride. And then we have things like, if you like racing, there's things called nitrous oxide. So there's NO2, which is called nitrogen dioxide. And then there's N2O2, which is called dinitrogen dioxide. And then there's N2O, which is called dinitrogen monoxide. So there are lots of different things, names for chemicals. But the point in chemistry is that the name tells you the formula, and the formula tells you the name. Like when you say the name of something in chemistry, you should be able to know what's in it. When you think of, in food, for instance, it'll say, oh, this is soup. Well, what the heck is soup? Like, soup doesn't tell you what it is. There's 1,000 different soups, right? We need to add some stuff in there to tell us exactly what's in the soup. And even that might not even describe what's going on. Like French onion soup. Well, that's got onions in it, but what else does it got? So let's get into it. So when it comes to nomenclature, we're going to talk about 3 different types of naming systems. We have ionic, we have covalent, and for covalent, we're going to only concentrate on binary covalent, which we'll talk about in a second. And then we have acids. Acids are some of the oldest known chemicals, so they have their own naming system. So how do you know you're dealing with ionic versus covalent versus an acid? So for ionic, you're going to have a cation and an anion, right? But you may not notice that by looking at it. So basically, we're looking for, is there a metal and a non-metal mixed together? If we have a metal and a non-metal mixed together, it's one of those days, then that is probably going to be an ionic compound. For covalent, we're looking at only nonmetals. So if it just contains nonmetals, then that's probably going to be our covalent naming system. And then for acids, acids have H plus cations. So if you see H as the beginning of the molecule, it's probably an acid and will require using the acid naming system. So the ionic naming system is the most complex. So let's just jump right into that first and talk about the different types of ionic naming. So, ionic. So the very first lesson in ionic is just what we're going to call simple binary, meaning we only have two atoms and there's nothing fancy about them. They don't have multiple charges or whatever. They're just going to be two atoms that we can just do the very bare minimum to name them. So when it comes to simple binary, the cation is very simple. It's just the name of it. So whatever it says on the periodic table is what you write. For the anion, that's going to be the name of it, but we cut out the end and we add IDE. So for instance, if we have Na with a plus and we add some Cl minus, this gives us NaCl, which if we want to name it, that is Na. So we look on the periodic table and it says sodium. So we just write sodium. This here is the anion. So we look that up and that's chlorine. So instead of chlorine, we get rid of the "ine" and we add "ide." And that's where the name sodium chloride comes from. Now we don't need to do anything else to this because saying sodium chloride tells the user who understands a little bit of chemistry that this is ionic because we have a metal and a nonmetal, sodium and chlorine, and that they are going to combine together in their ratio based off of their charges. And we don't need to tell what those charges are in the name because sodium and chlorine only have one charge, so we can just look that stuff up. If you go to your ion chart, which will be very helpful for your naming today, and tomorrow, and the weekend, because you have, tomorrow off. Another thing you can do is just match if you want to just do the matching game. If you look at, we talked about Na, well, we have Na plus, so you go looking for it, and you'll notice it just says the name there. It just says sodium. And then if we look down here and we're looking for Cl, you'll notice it doesn't say chlorine, it says chloride. So you can also, if you're using this polyatomic ion chart, you can also just make it a matching game where you go and you're like, okay, what's this thing called? And you find it on the table. What's this thing called? And you find it on the table, and then you just write their names. So this is simple binary. If we have the formula, we just simply state the name of the cation and state the name of the anion and change it to "ide." Or you can go to the chart and just find the cation and write its name down, and find the anion and write its name down. So here's another example. Say, for instance, we have some SrBr2. There's a 2 here because if we look on our chart, you'll notice that Sr is not on here, which is annoying. But anyway, strontium is one of the alkali earth metals, so therefore it has +2 as its charge. I tried to find one that had a lot of stuff on there, but apparently not. Come on, man. All right. So strontium is a +2 ion. We can also just go to the periodic table for that. New tab. Just have multiple tabs up. Your periodic table was in the previous module because we are studying the periodic table in the last unit. So anyway, there's strontium right there. It's in the second group. It has 2 valence electrons, therefore it's +2. So, and of course, if you want to print this out, you can write +1, +2, +3, -3, -2, -1, and then 0 if you want. So there's strontium. It just says strontium right there. So we just write strontium. So this guy right here is strontium. And we know that this is a thing and that this is a thing because of that capital letter. Remember, the capital letter tells us we're dealing with a new atom. And so we have SR, and that's one atom because it's a big letter and a little letter. And then we have BR, which is a new atom because we have a big letter and a little letter. So now we can go to our chart and we can look for BR. And you'll notice it says it right there. It says bromide. But a lot of you guys are like, well, what about the 2? And the answer is, remember, this is an ionic compound. So the 2 has to be there because this is a +2. This is a -1. So that's why that 2's there, remember, because they do the crisscross. So we don't have to say anything about the 2. We can just write strontium bromide. So these are simple binary naming. Now, if we want to go backwards, say for instance, we have the name of something and we want to write the formula, then we're going to look at our charges. So say for instance, we had some calcium. Sulfide. So we see the word calcium. We can go to our little chart here and we can look for calcium. And it's right there. Look at that. There's calcium. And it tells us our charge. It says it's a Ca +2. So that's Ca with a 2 plus. And then we have sulfide. So we can go look at our chart. And we can go looking for sulfide. And I find sulfate. I saw sulfite. And then there's sulfide. Make sure you're actually matching the correct one. So this one says sulfide. So we want this one. And that says S with a -2. So now we just need to put these guys together to balance their charges, just like we did in chapter 7. Now we could use crisscross, but if we do that, we would come up with Ca2S2, which is not right because remember we want the simplest ratio with ionic. So this is just CaS. And that's how you do simple binary. They're not difficult. The difficult part is balancing the charges. And that's why tonight you'll notice that you don't have a, or tonight and tomorrow, on the module, you don't have the quizzes. I gave you guys an actual written assignment, which we'll talk about more when we're done. And that's because I want you to actually like physically write everything out and not just guess multiple choice. So today's attendance assignment is not a quiz because I needed you guys to actually write all this stuff out. So it says attendance quiz, but it's not a quiz. So you'll click on this and you'll see that it has a PDF. Now, there's a bunch of ways that you can do this. You can print it out, or you can just simply do it on a piece of paper and you can scan that and then send me that, or you can just simply take a picture of it with your phone, whatever's easier for you. I set this up so that it will accept almost anything that you submit as far as file-wise. So like JPEGs or whatever, MP4s, whatever your particular thing is. But yeah, if you don't want to print this out, that's fine. If you just want to do it on a separate sheet of paper, that's completely fine. But if you want to print it out and then show me the picture or scan it, that's fine too. If you do have the ability, like I do, to like write on the screen, and that's fine too. And you can send me that. The problem I had with, because one of the options, you guys might, I don't know if you guys are Google School, but you might want to be like, oh, okay, well, I'm going to use Google Docs for this. And you want to be like, oh, it's a PDF. Well, I'll just open it in Docs. And that's fine. Oh, I don't have it on this computer. It'll screw up all those, it'll screw up all these formatting. So you can try that if you want. I tried it earlier. I didn't like the result. So it's up to you how you do that. But this thing has almost every type of naming on it. So let me try that right now where it says, there we go. So let's open with Google Chrome. Oh no, that's what I want to do. Docs. I'll just check real quick to see how bad it is. Yeah, it's not doing great. So it's up to you how you want to do that. I'm perfectly fine with just, screenshot, whatever. It's more about you just doing it with your hands on instead of guessing on a quiz. Because we need to use this for the rest of the semester and then next semester as well. So that's simple binary, going from the name to the formula or the formula to the name. So if there's simple binary, binary just means two atoms. Then what else do we have? Well, we have polyatomic ions, which is where the name of your chart comes in. Polyatomic ions. These are things you've heard of before, but basically poly, as you guys know, means many. So we have many atom ion. Atom ion. There's my brain getting ahead of itself. What do I mean by that? Well, if you just have, say, for instance, sulfur, sulfur is just a 2-. But sulfur can get attacked by that booger oxygen, and it will form this thing here, which altogether has a -2 charge. And it can also get together with this guy here, which altogether has a -2 charge. This guy has a name, it's called sulfate. And this guy has a name, it's called sulfite. So what a polyatomic ion is an atom has gotten together with some other atoms in an attempt to try and balance out their octets, and it didn't work out and they didn't quite finish, but they give off this charge which they can then use to attract other atoms. So that is why I gave you guys this chart, because I don't want you to have to memorize all those things, especially considering that, this is the summertime. And we're only going to be really on this for a day or so. So that's why this is called the polyatomic ion chart. As you can see, when it comes to positive ions, there aren't many polyatomic ions. There's really just one that you guys need to know, and that's ammonium. Ammonium is ammonia, NH3, that has gained an extra hydrogen on there, which ammonia, NH3, would be neutral. So this extra hydrogen makes the thing act as if it was positive. And so NH4 is a +1. But because of oxygen, there are a ton of negative polyatomic ions. Oxygen is just a booger. It is very, very electronegative, but it's not like fluorine where it's so electronegative that it can actually steal the electrons off. It just gets in fights with people over their electrons and ends up making just a ton of polyatomic ions. As you can see on here, there's only a few things like bisulfide or hydrogen sulfide. cyanide, and there should be a couple others on here that got left off. Oh yeah, so ferrocyanide. There's also thiocyanide that don't have oxygen on them, but basically they're just atoms that are combined together to form an ion. As this complete unit. But the naming rules are still the same. So if, say, we had some sodium sulfate, we're still going to figure out that this is a ionic compound because sodium is a metal. And then this mess right here is probably not going to be sulfur oxide because we don't know any naming system like that. So what we want to do is anytime we see something weird, we want to go to our chart and we want to look for it. And so what is that SO4 stuff? Well, it happens to be right there. And you'll notice it says sulfate right there. So we just do the exact same rules. This guy is sodium and this guy is sulfate. And that's it. That's all we need to do because, again, with ionic naming, it's really just a matching game. We're just writing down the names that we see on the chart. That's it. So if you've ever seen Epsom salt is MgSO4. Oh, sorry, there would be a 2 here. Epsom salt is MgSO4. And so what is MgSO4? Well, Mg is our cation, and there's SO4. So that would be, we looked that up, that's magnesium. And then that's sulfate. But what about if you see something like this, where you see calcium, and then there's a parenthesis, and then it says like that, or that's a 2. What is going on here? And the answer is nothing different. It's the exact same thing. This is still our cation, but the reason why there are parentheses here is because if we go and look this up, if we go and find NO3, you'll notice that it says NO3 is nitrate, and it has a -1 charge. And our magnesium has a +2 charge. So to balance these out, I'm going to need 2 of these things. So I don't want to write it CaN2O6 because N2O6 is not nitrate. So we don't do that. We don't distribute this 2. Even though this 2 is multiplying everything by 2, we write it down there to say that there are 2 nitrates. That's why there's parentheses there. So this is still just calcium. This is still just nitrate. We just write down the name that we see on the paper. Now, obviously, going from the name to the formula, we're going to have to balance our charges, and that's when we're going to have to put the parenthesis in there if we need it. So say, for instance, we had some aluminum. Do we have borate on here? We do, okay. Borate. We just go look for aluminum on our chart and see what it says. It says aluminum is a +3 charge. So we do aluminum, it has a 3+ charge. And then it says borate. And so we're just going to go look for borate on our chart. And so we go looking for borate. And there's borate right there. And it says BO3 as a -3 charge. So we go BO3 as a -3 charge. And of course, then we put them together according to their charges. So that guy goes there, that guy goes there, but they're both 3s. So we just get rid of them. And we write BO3. Now, a lot of people are like, what about this 3? And the answer is, don't even worry about it. Remember, this thing right here is acting like one thing. And this guy right here is acting like one thing. So we don't care about that 3. We just look at the charges, okay? So let's do some more examples here. Here, I'll do some from your paper. Do some of your homework for you. That guy right there, what's that? What's this BAMNO4 stuff? Well, let's well, we know that this is ionic because barium is a metal. Let's see if barium's on our paper. Yep, there it is. There's barium. Barium says it's a +2 charge. So this is going to be Ba, barium. And then what is this ugly mess right here? Well, there's another metal, so there's another clue that's ionic, but it's in parentheses. So that's telling us this is probably a polyatomic ion. So let's just go ahead and go look for MnO4. And, oh, it's not on here. All right. Oh, wait, no, there it is. I just can't. It's not in alphabetical order for some reason all of a sudden. Look at that. A, B, C, P, and then C down here. I don't know, maybe whatever. Permanganate is what this is called. So we're going to call it permanganate. And that's it. That's all you need to do. Permanganate. So this one right here, what's this? This is cadmium. Now, cadmium is going to require us to do cadmium. It's going to require us to look something up because you probably don't have cadmium on here as on your chart. So what we want to know, and this is going to be our next thing that we're going to talk about, is you'll notice that D block elements have Roman numerals, and that was the very next thing we're going to talk about. So we'll come back to number 3 in a second, because this is cadmium and this is sulfite. But the question is, which cadmium is this, or is there more than one cadmium? Because as you guys can see on your chart, we have one copper here, but we also have a copper there. We have one gold there, but we also have another gold over here. We have one iron there, we got an iron there. We got lead here, but we also have a lead there. There are 2 tins. So there's lots of multiple charges there. Now, that's a typo on my part. I meant to make that not cadmium. I meant to make that copper, but you know, that way you could use it on your chart. And on your test, I make sure that everything's on your chart. So anyway, we would want to look up, does cadmium have multiple charges? So, you know, obviously, since this is digital, feel free to look this up. Cadmium, there we go, ions. So cadmium does +2, it looks like. So you don't have to worry about the Roman numeral on that one. So you can call it cadmium 2, or you can just write cadmium. But we'll talk about that right now. All right. So let's go ahead and talk about Roman numerals. Let's actually get some notes on here. So then we have Roman numerals. So what is the point of the Roman numerals in ionic naming? Well, some things have multiple oxidation states. So for instance, iron exists as both +2 and +3. So when we tell these apart, we need some way of differentiating between them. So this guy is iron 2, iron Roman numeral 2, and this guy is iron 3, Roman numeral 3. Now, I picked this chart too because it has the old names for a lot of these things. For instance, you'll notice that iron 2 is called ferrous and iron 3 is called ferric. So you may find, it's very rare, but you may find them, instead of it calling like iron 2 or iron 3, it might say ferric or ferrous. So why do we need to tell these apart? Well, let me show you. Say, for instance, we took some iron and we reacted it with oxygen. Well, we could most of the time get Fe2O3. But some of the time, very, very rarely, we can get FeO. Well, why is this a big deal? Well, this is rust, and rust is pretty worthless. There's only a few examples of what we can use rust for. And this is ferrite, which is a very handy magnetic mineral that can be used for all kinds of things. One of its best uses is in computers as a voltage regulator, which is pretty cool. So what's the difference here? Well, the difference is going to be the charge of the iron. In this case, we have 2 irons with 3 oxygens, and oxygens are all -2. So these guys must be +3. Because remember, this guy has to add up to this guy. So 6 and 6 is that. So this guy is called iron 3 oxide, otherwise known as rust. And this guy is just 1 iron and 1 oxygen. So that's going to be +2 -2. That's going to give us iron 2 oxide. So if you were going to go read these labels, they would obviously look very different. Rust is rusty, ugly, red color, powder, and ferrite would be a dark grayish black, like gunmetal, and it would have magnetic properties and whatnot. And so if we just called them iron oxide, we would think they were the exact same thing. But this way, it lets us tell them apart. So with Roman numerals, the most difficult part of that is figuring out which one you have. And the way you do that is you look at the charge of the anion. Now, most of the time, to add to our notes here, Roman numerals only apply to cations. So we don't have to worry about that on anions. So when it comes to figuring out which Roman numeral you need, we're going to look at the anion. So say, for instance, we have some Cu2SO4. So that guy right there is our cation, and this guy right here is our anion, and that's copper. And this guy is, if you guys don't remember, is sulfate. There it is right there. So we write sulfate. But the problem is when we go look at our little chart here, you'll notice that copper is on here twice. There is copper right there, copper 1, and there is copper right there, copper 2. So which copper is this? Well, let's take a look. We have 2 coppers, and we have 1 sulfate. When we look at our chart, sulfate is in our divalent electronegative, otherwise known as -2. So that means the 1 sulfate is -2. So these 2 x's, so some number times 2 minus 2 equals 0. So what must this be? This must be +1. So this is copper 1. And if we look, you'll notice it says copper 1. Now, if you wanted to write cuprous, you could. If you wanted to be like, old-timey and say cuprous, you can. That's fine. It's just modern day, you won't see that much anymore. It depends on the substance. If it's like a mineral that's dug up out of the ground and just purified, then it might actually have its old name. So a good example of this is copper 2 chloride. So this is copper 2, and that's chloride. We know this is copper 2 because we have 2 chlorines. Chlorines are -1, so this thing must be +2. So this is copper 2. Well, when I buy copper 2 chloride from Flynn Scientific, it will come as cupric chloride. It'll say it on there. But it's funny because it says cupric chloride, and then right underneath it, it says copper 2 chloride. So I guess, as a chemist, they need to be told like which one's which. So another thing, if you want to do, if you have printed out there we go. If you've printed this out, or if you have your own, another thing you can do is write the charges in here. So these guys are all +1, these guys are all +2. Scandium tends to just do +3, but iron, you can write the +2 and the +3 in there. Cobalt is +3 and +6. Nickel just tends to do +2. Copper is +1, +2. Silver is just +1. Zinc is just +2. Gold is +1, +3. Tin is +2, +4. Lead is +2, +4. So you can write them on your periodic table if you've printed it out. If you're just using it digitally, then you can do that. Why are you blinking at me? All right. So these are Roman numerals. So the hard part with the Roman numerals is going from the formula to the name. But when you have the name, it's not very tough because then you're just matching again and then balancing the charges. So say, for instance, we had some iron 3 carbonate. Then we're just going to find iron 3 on here. And you'll notice that iron 3 is Fe with a +3. So we just do Fe with a 3+. And then we're going to go looking for carbonate. So we go looking for carbonate. And hey, it's right there. We didn't have to move the screen. It says CO3 has a -2. And remember, we do our crisscross. And so this will be Fe2. And then we have CO3. So we're going to use a parenthesis, CO3. And we have 3 of them. So that's it. And that's all there is to ionic naming. It's the most elaborate of the naming systems. The next one is going to be very simple. That's why we've taken a long time on it, but the next 2 systems are really quick and easy. So that's ionic naming. So then binary covalent. Now I say binary covalent because covalent molecules are all over the place as far as how many things are in there. So after a certain point, they start getting their own naming systems for each classification of chemical. Now we're not going to do any of that here in this level of chemistry, so we're only going to be worrying about binary covalent. So what is binary covalent? 2 nonmetals hanging out with each other. And this guy right here is probably the one you've said most of your life, and you didn't know you were actually saying a binary covalent chemical name. But this guy right here is carbon dioxide. Because what we do in binary covalent is we use prefixes. With ionic, we were not interested in how many there were there because there was only one possible combination. But as you saw with the nitrogens, we have NO, we have N2O, we have N2O2, we also have NO2 and N2O4, there's N2, there's NO3, there's NO2. You'll notice that there's a ton of different combinations of NO. So how do we tell them apart? Because there's not just one way that N and O combine. And the answer is we use the prefixes. And it's only going to happen if we have two nonmetals. So what are the prefixes? One is mono. So if you've ever heard of mononucleosis, that's what mono means. It means one. Two is di. You've probably heard of a bicycle. Well, this is not that root, which I think is Latin. This is more kind of a mix of a couple different languages, as you'll see when we get to 4. 3 is just like you've heard in geometry, it's tri. 4 is quad, right? No, it's tetra, because it's got some Russian influence on here. If you've ever played the game Tetris, you know that everything in Tetris is made of 4 blocks. And if you want to get a Tetris, that means you have completed 4 lines at once. Tetra means 4. And then it goes back to your ones that you're familiar with from geometry. Then we have penta, and we have hexa, and we have hepta. Sometimes there's septa for 7. This is hepta. And then we have octa. And then for you Italians out there, we have gramma, nona, and then we have deca. And then after deca, we tend to, there are dodecas and things like that, but it tends to start to just go into the naming system of that particular molecule. Like for instance, gasoline, you've probably heard is called octane. Well, that would have, you know, octa, nona, and all that kind of stuff in it. But again, it has its own name. So there's only one other rule besides use prefixes in front, and that is mono is only on the second one. So we don't say monocarbon dioxide, we just say carbon dioxide because monocarbon is redundant. When you say carbon, you're saying at least one carbon. And if you needed to say more than one, then you would have given it a prefix. But when you say, like say for instance, CO, the reason why this isn't monocarbon monoxide the reason why this isn't monocarbon monoxide is because that would make it sound like it was ionic if without saying the mono. So we don't say monocarbon monoxide, we just say carbon monoxide to differentiate it between an ionic compound and a covalent compound. So that's carbon monoxide. So if we want to look at all those big, massive, nasty things that we had before, N2O is going to be dinitrogen, and then monoxide. Hey, and then our old favorite, H2O. You've probably seen this on like a meme on the internet. This is going to be dihydrogen monoxide, which is the name of water chemically. Now, these are really easy to do if you have the name and you're going to the formula because we don't care about the charges at all. So say, for instance, I had some penta, well, let's see. Say, for instance, I had some triphosphorus decoxide. Well, it says triphosphorus, so that's P, and tri is 3. And then it says decoxide. Well, oxide is O, and dec is 10. That's all there is to it. Now, and then you know you're dealing with a covalent compound when you have two nonmetals. So if we look at number 1 here, we know that that is a covalent compound because that right there is boron. You gonna do it here? That right there is boron. That right there is oxygen. And so we're going to call this diboron trioxide. Now, if you were to make the mistake of calling boron a metal because of the way your periodic table is written or whatever, since it says metalloid, and you were to call this boron oxide, there is a case made for that. The electronegativity difference between them is large enough to make it ionic, but just that. It is barely enough to make it ionic. So most of the time you'll see this as diboron trioxide. But if you were to call it boron oxide, I understand why you would do that. Okay. So that's ionic naming, that's covalent naming. Pretty simple. What is acid naming? Well, you've heard of acids. Acids have been around for all kinds of time. Acids are actually some of the original names where everything comes from. That whole cupric and cuprous stuff comes from the way it reacted with acids. So what is acid? Turns out acid is hydrogen ions. If you have hydrogen cations, you are an acid. So acids had names from thousands of years ago. So we had to kind of adapt the acid naming system and the ionic naming system around kind of this acid system. So for instance, HCl in its ionic name, this would be hydrogen chloride. But because we see this hydrogen here, this is an acid, so it has the name hydrochloric acid. Now, it doesn't look like we're saving any syllables, and that's because we're not trying to make it smaller. We're just trying to tell people that this is an acid, and it's much more dangerous than hydrogen chloride. So, what is the acid naming system? It's actually pretty simple, okay? So because H plus is always the same in every single one of these molecules, this is just taken care of with the word acid. So rather than writing the name of the cation hydrogen, when we say the word acid, we're saying hydrogen. So every other type of acid is going to depend on the cation. Or sorry, the anion. The negative one. So because there are 3 types of ion or anions, there's ides, there's ates, and there's ites, we have 3 types of acid names. So in the case of HCl, this is chloride. So for ides, we write hydro, and then we write its name. But instead of ide, we drop the ide and we write ic acid. So this guy right here is hydrochloric acid. HCl equals hydrochloric acid. If we have some chlorate, which is HClO3, we drop the hydro and we just write ic acid. So since this is chloride, that's hydrochloric, And because this is chlorate, this is just chloric acid. And then finally, if we have some chlorite, which is ClO2, then we get rid of ic and we write us acid. So this is right here, chlorite. So that becomes chlorous acid. And the way I like to think of it is I hide underwater, so hydro, and I ate it and it tasted icky. And righteous acid, man. See? Yeah? No? Maybe? All right. You can obviously just write this down and look at it when you're doing it. So let's go ahead and look for an example on your little homework here. So this right here, you could either do binary or you could do an acid name. Either one is correct. So these guys right here are acids. Get rid of this stuff. Take a snapshot. So what are the names of these guys? Well, both of them are acids because we have our hydrogen ion here. So now we have this as our anion and this is our anion. So looking at our polyatomic ion chart, SO3 is a sulfite. So because this is sulfite, ites are us acids. So this is sul, and then you put the UR back, sulfurous acid. This one right here is bromide. It's an ide. So because ides are hydro, we write this as hydrobromic acid. And that's all there is to it. Now, if we're going the other way, did I have it? There we go. We got acid right here. This is nitric, so there's no hydro, so this is 8. So we're going to go looking on our periodic table for nitrate. And there's nitrate right there because it's NO3. So NO3 has a -1 charge. Acid is hydrogen. So they're +1 -1. So this is just HNO3. And that's how you name most of the compounds you'll deal with in chemistry. But that's it for what we needed to talk about today. Are there any questions before you are released for your 3-day weekend? Okay, everybody. I'm going to hit the stop record.